If you've ever dreamt about digging to the center of the Earth, you'll want to meet the Red Boar 100, the biggest and baddest drill in the world. Light assault vehicles are essential to modern infantries. The Lav 3 ranks with the best of them. Recycling machines work together to take care of all that stuff we toss into the box, no matter what it's made of. Stirling engines have been around for 200 years, quietly waiting to change the way we power pretty much everything. Let's take a look inside these machines and see how they work. This is the Red Boar 100, one of the most powerful drills on the planet. For blasting tight spaces like mines, city sewers, and subways, this type of drilling is faster, cheaper, and cleaner than the old-style drill and blast. It cuts an 8-meter wide hole, hundreds of meters deep, through solid rock. Big enough to swallow trucks. Lots of trucks. They call the 100 a raise bore drill. Here's why. This machine drills up, raising its cutter toward the surface. Its massive cutting tools called a reamer, driven by hydraulic cylinders that crank out 1,000,000 kilograms of thrust. The same force blasting from NASA's latest rockets. As mines expand, they need extra vent shafts for workers and access tunnels for heavy gear. Here in northern Quebec, the Queen Louise is drilling a new ventilation shaft at a gold mine. Let's see how it works. First, the reamer is positioned in the target zone of an existing shaft, ready to be attached to the drill pipe. The machine up top has to punch a pilot hole through almost 1 kilometer of rock to hook up with the reamer below. A lot easier said than done. Here's the problem. Think how much effort it takes you to push a small drill through a piece of wood. Now, imagine the strength required to drill through almost 1 kilometer of solid rock. First, drilling the pilot hole through rock this hard can easily deflect the cutter and force the drill pipe way off target. And second, pulling the reamer up through so much rock has to be done right. So this part of the operation needs both strength and precision. Electric motors power hydraulic cylinders that generate enough thrust and torque to keep the pilot drill turning. As the bit descends, 2-meter drill sections are added piece by piece, pushing it down further. Each of the sections feature a unique thread design to deal with the machine's powerful torque and thrust. The threads work with the torque to lock the sections together. This is critical in helping the drill stay straight. If the drill is deflected even by a small amount, it can result in the drill missing its target. Small mistakes, when amplified over hundreds of meters, become big ones. So all the machine's power needs some precise management. If it deviates more than 1%, that's 10 meters for every 1,000 it goes down. Pulling back up becomes a real problem. So if the drill starts to go off course, the operator uses the machine's steering function to get it back online. They don't let rookies drive this thing. Once the pilot hole is complete, they're ready to hook up the big guy, the reamer. With hundreds of jagged titanium teeth, strong enough to tear through rock. But pulling the reamer up through such a long distance has to be done right. Mistakes down here cost a lot of time and money. On a good day, this machine cuts through over 1 meter of rock in an hour. So, if all goes well, this hole will take about 6 months to finish. Much faster than traditional methods. In order to produce the force it needs to pull, a raise bore drill uses the earth below it for leverage. This innovation allows the red bore to generate over 1.7 million kilograms of pulling power. All the falling rock crashes to the mine floor and is removed by loaders and trucked out through tunnels. The machine is so automated, you only need a couple of operators up top and an observer down here keeping an eye on things. If something goes wrong, he gets on the horn pronto. Back up top, whether adding sections of drill pipe going down or removing them coming up, you need a hand. In this case, a powerful robot wrangles each 1,200 kilogram section. On a hole this deep, that adds up to over 500,000 kilograms of steel. The final challenge is ground control. Precision drilling the main hole up is as vital as it was drilling the pilot hole down. When you're cutting an 8-meter hole, you have to make sure it's going to stay 8 meters. Any wider, it'll crumble, needing very expensive support work. So drillers have to know what kind of rock they're dealing with and be able to react quickly to underground surprises. The Red Bore 100 weighs in at about 75,000 kilograms. And falling down the same hole it's digging would be very bad. So this machine starts every job with structure and support. That comes in the form of a poured concrete foundation and steel girders that span the area over the projected opening. It'll take the Queen Louise another few months to finish up here. When completed, the hole is secured and handed over to the mine. And she moves on to her next job. Depth, power, and precision. When you call yourself the most powerful drill in the world, you better deliver. And the Red Bore 100 sure does. This is the LAV-3. A light assault vehicle used by modern mechanized infantries. It's called light because it weighs less than a tank. But it's plenty tough and can handle the assault part too. At this Canadian Forces base in Petawawa, Ontario, the men and women of the 2nd Mechanized Combat Brigade are training for a tour of duty in Afghanistan. The conditions may not be identical between the two countries, but the challenges for the machine are the same. Move across rugged terrain without breaking down, find and destroy threats in the hills, and work as a team with the soldiers it carries. Armies around the world rely on this machine because of the way they protect and deliver troops. Let's see how it works. The LAV-3 is a miniature army base on wheels. It comes equipped with tires and a suspension system that lets it climb pretty much whatever it wants. And an engine that can top 100 kilometers an hour. Not bad for a machine that weighs 5 tons more than a school bus. These mechanical details make sure troops arrive fast, safe, and ready to fight. Whether hunting or fighting the enemy, gathering information, or rebuilding vital infrastructure, there's no substitute for feet on the ground. And delivering those feet is what this machine is all about. The start of every mission begins with a load-in. Supplies are carefully laid out for pickup, especially these, rounds for its primary gun, the Bushmaster M242. Weapons, ammunition, rations, water, and other equipment crammed into every available nook and cranny of the hole, the compartment where the soldiers ride. Once they leave base, troops are on their own, so they can't leave anything behind, including their most important cargo, themselves. The carrier hold of the LAV-3 takes up to 7 personnel, and it's a tight fit. Add to that the machine's crew of 3, commander, driver, and gunner. Carrying that number of troops is a big advantage. Smaller vehicles may be fast and cheap, but they carry fewer personnel, and they don't offer nearly as much protection. The LAV's thick outer skin is designed to stand up to 50 caliber fire and more. Fully armored, the LAV weighs in at a hefty 17 tons. Its large fuel tanks allow it to travel almost 500 kilometers without needing to refuel. And it can maneuver well in tight spaces. Critical for working in urban environments and for getting the job done no matter what surface it's on. The tires are positioned close together to mimic tank tracks. This allows the LAV to cross a 2-meter-wide trench. And onboard compressors can deflate the tires for slick terrain where extra surface area is needed. Fully independent suspension keeps the ride rolling. But tough terrain isn't the real threat. What's on it or under it is. These days, that means improvised explosive devices and car bombs. If there's suspicious activity on the road, 2 hatches allow troops to keep an eye on anything sneaking up from behind. The rest of the crew keeps focused on what's ahead of them. With crack soldiers on board, it's easy to stop, establish a perimeter, and check out potential trouble. And if you're heading into sniper country, batten down the hatches. From inside, drivers and gunners use advanced periscopes to get clear views without exposing themselves to enemy fire. Driving the machine is pretty much like handling any heavy-duty vehicle. It comes with a big steering wheel, gas pedal, brake, and gear shift. Here's where the similarities end. The Bushmaster M242 autocannon, a weapon that's as reliable as it is powerful. Most machine guns use a shell's explosive recoil to eject empty casings and load the next round. But in guns powered by explosions, a lot can go wrong. Heat is a problem, and so's jamming. If a casing gets stuck and the next bullet can't load, you're no longer in the fight. This is not an option for the Bushmaster. So on this gun, rounds are loaded and ejected with a chain drive that's powered by a small motor. Even if a shell gets jammed, the chain just pushes it out. It's the action of the chain that drives the bolt back and forth. The shape of its barrel helps the M242 overcome another automatic weapon challenge, overheating. It's fluted, and this helps by exposing more surface area to the cooling air. The gun spits out massive shells at more than 3 times the speed of sound and has an effective range of 2 kilometers. With all this power and mobility, light assault vehicles have become a vital part of modern infantry strategy. LAVs normally conduct offensive operations as part of a combat team. The machine's high mobility and toughness make it ideally suited to support unit movement. Once troops hit the ground, the LAV turns into a mobile command center, at the ready to provide backup in any way it can. One thing the LAV-3 does not do a lot of is retreat. When combatants see a line of these guys rolling in, their usual response is to turn and head for the hills. Speed, handling, heavy armor, big guns, and a belly full of soldiers makes this a machine to be respected. A typical Canadian uses 4 trees worth of paper annually. Americans toss enough aluminum cans away every month to rebuild its entire commercial air fleet. And in 1 year, Europe goes through about 10 million tons of newsprint. Recycling just 1 ton of newspaper saves 19 trees, 3 cubic meters of landfill, and 29,000 liters of water. Good thing we're becoming better recyclers. Every year, more and more materials are collected worldwide to be sorted and transformed into something new. And the single-stream recycling machine helps make that possible. It handles paper, glass, metal, cardboard, and plastic. Let's see how it works. Step 1. The material arrives. A front-end loader pushes everything onto a conveyor belt. There's a lot of it, and it's mixed up with tons of garbage that has to be manually removed before the recycling materials can enter the machine. Now, all this stuff has got to be sorted. No small task. Fortunately, this machine is a master sorter. The challenges in here are always the same. Find and get rid of the bad stuff, and then sort the good stuff into different piles. It comes armed with 3 sorting screens for cardboard, newsprint, and magazines, as well as a set of magnets to handle metal. First up, the cardboard screen. It's made of rotating steel discs. As the discs spin, their spikes knock pieces of cardboard into the air and onto a conveyor. The cardboard flows onto a bundling area. It's on its way to becoming new packaging, like egg cartons. The rest of the material moves on to stage 2. The plastic, metal, glass, and paper arrive at the second sorting screen. This is the newspaper one. It sorts different grades of the material using these rubber discs. After being separated, it's sent to paper mills to make more newsprint or toilet tissue. Glass, metal, and plastic roll off the screen and move on. Magazines and other materials like flyers fall to the same conveyor. They're made from different fibers than newspapers and need their own sorting. And that happens at the final screen. The heavier paper sticks to these rubber discs with the help of fans. This type of paper is recycled into products like gift boxes, game boards, and greeting cards. That's it for the screens. Now it's time for the magnets. The machine has to separate metal into 2 groups, ferrous and non-ferrous. Ferrous metals, like steel, are magnetic. Non-ferrous metals, like aluminum, copper, and tin, are not. So to start with, a big magnet is used to take out the ferrous materials. Then, the machine targets aluminum, an extremely valuable recycling material. You can make 20 cans from recycled aluminum with the same energy it takes to make 1 can out of new material. Tossing out just 1 is the same as spilling half a can of gasoline onto the ground. To separate aluminum, the machine needs help from the electrical phenomenon called an eddy current. The aluminum picks up a charge as it passes over this magnet. They now both have the same charge, so they repel each other. Same as when you try to push 2 magnets together. Once separated, the aluminum is bundled, then shipped to be melted down and repurposed. Finally, the plastic and glass are separated by hand before further processing. The machine ensures that about 95% of what it started off with gets recycled. The basic materials of paper, plastic, and metal are repurposed into everything from carpets and ski jackets to beer cans, takeout containers, and home insulation. And that's good news for everyone. You're looking at a Stirling engine. This model, first used as a water pump, has been working for over 100 years without a hitch. It's among the most efficient engines ever invented. First built in the 19th century, the full potential of the Stirling is finally being realized. It can convert almost any source of heat into energy cleanly and quietly. Anywhere you need electricity and heat, the Stirling engine may be what you're looking for. And new versions of this machine may soon be powering our homes. Let's see how it works. A basic Stirling engine needs a heat source, a cooling source, and a piston. That's about it. When you heat a gas with fuel, it expands and pushes a piston. Cool a gas with, say, water or air, it contracts and pulls the piston. And if you're using waste heat, there's no direct combustion or emissions. It's also very quiet. This model is a two-piston version. The first piston drives the engine, and the second is harnessed to power a water pump. All it needs to work is heat from the wood stove. In theory, you could use a Stirling to create power from anything that produces a constant source of heat, like the inside of your computer. Designers are working on a small Stirling to power the CPU fan with waste heat, and automakers have tinkered with Stirling engine cars since the 70s. So if the Stirling engine is so amazing, why isn't it powering everything? Because it has a number of challenging disadvantages. The main ones are they're expensive to build, and the older versions don't produce much power for their size. Another one is that they take time to warm up and start their engines. Who wants to wait 20 minutes for their car to start? But for home applications, there is change afoot. Rather than pump up and down, it uses heat from a gas flame to move these 4 pistons that are connected to a very special gear called a wobble. This converts Stirling power from up and down into round and round. And it spins a small generator that pumps out electricity directly to your house. This mini power plant is being rolled out in central England. It's called a WhisperGen. It's fed by gas and connects to a home's central heating supply. But as it's heating the water for your shower or the radiators for warmth, it's also producing electricity. Inside each machine, there's a generator that's wired into the home's electrical system. If you're using electricity while your WhisperGen is on, it will help power your lighting, TV, and other electrical appliances. About the size of a dishwasher, this machine is very efficient. It converts about 90% of the fuel it gets into usable energy. A lot of the electricity we get over the grid comes from power plants that are less than half that efficient. So these things save big on bills and emissions. It won't be long before Stirling engines are popping up in all sorts of places. Solar plants, jet engines, you name it. Pretty cool for a machine that's 200 years old and virtually anonymous.